Welcome. This is Emmett, and today's video we'll be tackling this problem. For more unique problems Mari and I created and solved, visit the link in the description and check out the rest of our videos. Okay, so y equals x to the 1/2 is bounded from x equals 0 to x equals 4. Each vertical cross-section of this region is the area under the graph of y equals e to the x, bounded by x equals 0, and the y value of y equals x to the 1/2 at that cross-section. So think of the x bounds for y equals e to the x as the vertical distance of the curve y equals x to the 1/2 at that specific cross-section. So what is the volume of this region? So pause, try it out, and get back to the video when you're ready. I'm going to start by drawing this out. So I drew the x and y axes beforehand at a slant, and you'll see why it's slanted in a second. And then we also have the equation y equals x to the 1/2, or square root of x, in this plane. And then we also have the bounds from x equals 0 to x equals 4. After this, the problem says how each vertical cross-section, so these are vertical cross-sections here, is the area under the graph of y equals e to the x from x equals 0 to x equals the y value of y equals x to the 1/2, this blue line here, at that cross-section. And so what that means is instead of each of these cross-sections simply being lines, where you're summing up these infinitely thin boxes here, just to show you, since dx would be infinitely thin and you'd have an infinite amount of boxes, instead of this, each cross-section is an integral, a 2D shape. So to show you what this looks like at one specific cross-section right here, where say x equals 3, I'm going to overlay some labels. Okay, so I've just overlaid this x and y axis, which is separate from the original slanted x and y axis here. And so this cross-section here, the area of this cross-section, is the area under the graph of y equals e to the x from x equals 0. So x equals 0 is right here, not to be confused with x equals 3, which is for this x and y axis. It's the area under the graph, so from x equals 0 to x equals the y value at this cross-section. And so this y value is 1.73 because at this cross-section x equals 3 for this x and y axis, and then to get the y value along this blue curve, since its square root of x is the equation, you take square root of 3 to get 1.73. And so at this cross-section, the area of it is going to be the area from 0 to 1.73 under the curve right here. As you can see, it comes up to make this 3D shape under the curve of y equals e to the x. And so this area looks something like this. And so now you can picture that we have all of these integrals at each cross-section. And so when each of these cross-sections are multiplied by dx, which is an infinitely thin distance, you get this 3D volume here. And so this means that we have an integral of integrals. So we have the integral from 0 to 4 of what exactly? Well, unlike a function that gives the height at each cross-section, say like square root of x, or if you were to integrate regularly with respect to x, you get a height at each cross-section. So unlike that, we need a function that gives the area at each cross-section. And so how can we get the area of each cross-section? Well, looking at the example where x was equal to 3, what we did to get the area is you can take the integral from 0, because it's from x equals 0, to x equals square root of 3 at that cross-section, but just to generalize, it was square root of x, whatever x happens to be. And so it's the integral from 0 to square root of x of e to the x dx. And so this is the function that gives the area at one cross-section. And so if we want to integrate all of the areas together to get a volume, we take the integral from 0 to 4 of integral 0 to square root of x e to the x dx and then dx. Okay, so to integrate this, we can first integrate the inside right here. Okay, so the antiderivative of e to the x is just e to the x. And so this inside equals the evaluation of e to the x from 0 to square root of x. And so this equals e to the square root of x minus e to the 0, which equals e to the square root of x minus 1. So now we can plug this back into the parentheses right here. So we have the integral from 0 to 4 of e to the square root of x minus 1 dx. Now you can integrate this by hand with u-substitution of root x and then integration by parts, but I'm just going to use my calculator for the sake of time. So my calculator gives a final answer of 12.778. Hopefully taking integrals into 3D was interesting. Thanks for watching and have a good day.